Good morning, all of you. Today we are going to discuss mathematical modeling of rotational mechanical systems. Okay, Unit 1, Subject Control Systems. Okay, so in the last class we have discussed mathematical modeling of translational mechanical systems. Okay, so today we are going to discuss rotational mechanical systems. Right? See, See, rotational mechanical systems are similar to translational mechanical systems, except what all the terms we are using variables. What are the variables we are used there? Displacement, velocity, and acceleration are here in angular quantities. Okay, so in a translational mechanical system we return force equations. Okay, in this case we are going to write torque equations. So in rotational system the motion is around a fixed axis. Okay, whereas in translational mechanical system the motion is on a straight line, right? So in a straight line, right? So let us see here. So rotational mechanical systems, right? So generally we are write input as a torque, that is represented with T, and output will be, in this case, angular terms, angular displacement that is represented with theta, or angular velocity, which is represented with omega. Okay, so see here, in rotational system, the motion is around a fixed axis. Okay, so in rotational system the motion will be around a fixed axis. Okay, but whereas in translational mechanical system the motion will be in a straight line, right? So that's why we are considering all variables in terms of angular quantities. Remember this one, right? Okay, so what are the variables here? Variables of rotational system. Okay, what are the variables we have? The first one is you can say displacement. So here, see here, what you need to, I said already, this is angular quantities, angular displacement. Okay, which is represented with theta, right? Second one is angular velocity. Okay, so which is represented with omega. And third one is angular acceleration. Okay, you can name it either alpha or I'm naming directly A. Okay, angular acceleration, right? Right. Now elements okay Elements of rotational system. Elements of rotational mechanical system. So what are the elements we have? The first one, see, in this case we'll call inertia. Inertia element, which is represented with capital J. Okay. See here, the the major property of the system in which kinetic energy stores in rotational system is called inertia. Okay, so I will write this one here better. Now the property of system which stores kinetic energy in rotational systems is called inertia. Okay. Right. So what are the units for inertia? So okay, we'll discuss while writing the torque equations, we'll discuss that, right? Okay. Second one is damper element. Okay, so this is represented with same B. You can say torsional damper also, no problem. And third one is torsional spring element. Okay, so this is represented with K, right? So what are the elements in rotational mechanical system? We have inertia element, which is represented with J, damper element or damping coefficient or viscous friction coefficient, whatever you call, right? Then next is torsional spring, okay, element. So damper element, which is consist of friction of viscous friction, which is nothing but friction between surface and fluid, okay, and spring element, which is nothing but what it it has the property of elastic deformation, okay, as we discussed in the translational mechanical system. Okay, so almost similar, okay, rotational mechanical systems is almost similar to translational mechanical system. Okay, only few things will be changes, that variables will be angular quantities and the motion of the system will be, okay, around a fixed axis, whereas in translational system, okay, we have in a straight line. Okay, right. Now we'll see the one by one. So first one is inertia element. Okay, which is represented with J, and the units are, okay, units are, I can write here, units are kg per kg meter square. Okay, so inertia units will be kg meter square. These are the units, right? So here whenever torque is applied to inertia element, therefore that is called, we have inertia torque. Okay, then that is represented with Tj, for example, okay, is proportional to angular velocity. is directly proportional to angular velocity. So this can be written as Tj directly proportional to, okay, angular velocity. We can say omega, right? So see here, I will write the equation. So we need to write here torque equation, right? Okay. So let us consider a system. Let us consider a system. This is reference, and see, this is inertia element. Okay, now okay, now here torque is applied in this direction. T is a torque, and here is the displacement, and here is the velocity. Okay, now this is inertia element J. Okay, now let us write the torque equations here. Now a torque equations, I can say here, I will write, okay, torque equation A in terms of angular displacement. Okay, in terms of displacement theta, right? So what are the equations we have? See here, right? So torque is equal to J into d square by dt square theta. Okay, right? And second one, B is equal to, in terms of angular velocity, omega. So what is the torque equation? Torque is equal to, see, in this direction torque is applied, right? Okay, torque is equal to J inertia element into d by dt of angular velocity, right? Now, so where I can say, where T is a torque, externally applied torque. What are the units for torque? Torque units are, you have Newton meter. I'll mention this one. Okay, units are Newton meter, or you can say, if you convert this Newton meter, kg meter okay, meter square per second square. Okay, so Newton means what? Kg meter per second square. Okay, so already meter, so kg meter meter square per second square, right? Then inertia element. Okay, so inertia elements, what are the units? Units are kg meter square. Okay, next is displacement. What are the units of displacement? Radians. Okay, and velocity, angular velocity. So angular displacement, angular velocity d by dt of this one. So it is radians per second. Okay, and any terms, all the terms are completed here. Okay, right? So this is about inertia element. Okay, so you need to remember these terms, right? You need to remember these formulas whenever the torque is applied to a inertia element. Okay, right. Next term is damper element. come to damping I write better, damping element, okay, which is represented with B only here also, right? So here whenever the torque is applied to a damping element, then that is called damping force, I mean damping torque in this case, right? So damping torque directly proportional to the angular velocity. So damping torque I can write here, damping torque is proportional to angular velocity. Okay, so it's nothing but TB directly proportional to omega. Right? So let us see here. Right. Now we'll write the torque equations. Okay. So the first one, A in terms of angular displacement. So see, already whatever the frictions applied to a applied to a rotational mechanical system, okay, we already discussed in the translational one, that is what static friction, viscous friction and Coulomb friction. Okay, so all the terms will be applicable here also, same. Okay, so that is the reason I'm not discussing again here, right? Theta. So here torque is equal to, so this term we need to write. Okay, so before going to that, we need to draw a damping element here. Same notation, and damping element, and see here we have torque is applied T, and this is angular displacement theta 1 and angular velocity 1. Okay, another angular displacement 2, in this case omega, angular velocity 2. Okay, so this is called, named it B. Okay, damping element. What is that? Damping element or viscous friction coefficient, whatever you call it, right? So for this one we need to write a torque equation. Okay, so T is equal to, see here, torque is equal to, what is that? B into B into d by dt in terms of displacement we need to write first. Okay, so which is nothing but theta 1 minus theta 2 for this equation, right? Theta, see torque is applied here, so theta 1 minus theta t. If I consider B into d by dt of theta, where I am considering theta is equal to theta 1 minus theta 2. Okay, so where this is a displacement, right? So this is the damping torque equation for damping element in rotational systems. Okay, right. So what are the units here? Okay, commonly we'll write the units for all. Next is B. So writing the torque equation in terms of angular velocity omega, So torque equation in terms of, let us see the displacement. So what is that? B into V, omega, right? Omega 1 minus omega 2, this value is omega 1 minus omega 2. Okay, so where if I consider this value B into omega, where omega is equal to omega 1 minus omega 2. Okay, right. See here, I will like to write units of damping element. The damping units are, what are that? Newton meter second per radians. Okay, Newton meter seconds per radians simply. Okay, and you know all these values. Velocity, angular velocity is nothing but angular velocity, theta, and torque. So what are the units? Angular velocity is radians per second. This is displacement is radians. And what about torque? Torque is nothing but Newton meter. I am directly writing here Newton meter. Okay, these are the units. Right, second term also completed. Let us see the third element. What is the third element? Torsional spring element. So this is represented with K. So already discussed this one. See, spring element, or we can say stiffness. Okay, right. Let us draw the diagram for that one. So spring element, if I consider a spring element, right, this is a spring element, and here torque is applied, and displacement, angular one, is all are angular quantities here, theta 2 and angular velocity 2. Okay, so this is represented with K. Okay, this is the term, right? Here the whatever the force due to the friction, whatever the force applied on a spring element, it is called spring torque. Okay, and it is directly proportional to the angular displacement. You can say that I will write here Tk. Okay, that is what? Spring torque, torsional spring torque is proportional to angular displacement. Okay, so angular displacement. That is what I can say if I write Tk is directly proportional to theta. Okay, right. So let us write the torque equations for this one. Equations, torque equations, right? So let us take in terms of angular displacement. Theta, angular displacements. So what are the units actually? What are the units for the spring element, torsional spring element? So what are the units? Units are Newton meter per radians. Newton meter per radians. Okay. Okay. Anyway, now torque is equal to in terms of displacement I am writing here. So what is that? K into theta 1 minus theta 2. Okay, right. So if I still write this one, theta into K, where theta is equal to, I can say, theta 1 minus theta 2. Okay, theta 1 minus theta 2 in terms of displacement, right? Now second term, B, torque equation in terms of angular velocity omega. Okay, so what is the, see here, torque T is equal to k theta. Okay, so angular displacement, d by dt of angular displacement, we know that angular velocity. Okay, so angular displacement I can write integration of omega t dt, right? So I am writing here same. So for angular displacement, I mean to the angular displacement, torque is equal to k theta, right? So this term I will write k theta is equal to integration omega dt. Okay, so this can I will write as theta is equal to become a 1 by k integration omega t dt. Okay, so this is the velocity equation. See here, don't confuse here. So I written 1 by k, consider this k as a compliance. Okay, compliance value, which is nothing but, if I consider k, capital K, 1 by k, as per our requirement I am writing 1 by k value. Okay, or see this whatever the k value, if I consider in terms of electrical system capacitance, so k becomes 1 by k I can return. This is called compliance. Okay, so this term, it is called compliance. Okay, so compliance, k becomes 1 by k I can write, so that's why I directly taken 1 by k in this case. Okay, so this is the equation for angular velocity. Okay, torque equation for angular velocity, which is nothing but what? So torque is equal to 1 by k. Okay, so k value, theta value I am writing here, 1 by k integration omega dt, right? Now this is a torque equation. Okay, for angular velocity, where k is a compliance here, k becomes, I can write 1 by k. Okay, capital K or small k, 1 by k compliance it is becomes, right? Okay, right. So these are the three elements, okay, used in the rotational mechanical system. Okay, right. So next we will see D'Alembert's principle, okay, for rotational mechanical system. Okay, next we will see D'Alembert principle for rotational mechanical systems, right? Okay, so already we know that in a translational mechanical system we discussed about D'Alembert principle. Okay, here also we are applying the same principle. Okay, D'Alembert principle says that see, sum of externally applied torques is equal to sum of the opposing torques. Okay, or for any body the algebraic sum of externally applied torques and opposing torques at any instance is 0. Okay, so only change here, translational and rotational mechanical system, what is the change? There we are used the word force because motion will be in a straight line. Here motion will be in a fixed axis. Okay, so that's why here we are using torque and their force. Only D'Alembert principle, here we are using torque, the word torque, right? So I will write definition once again, similar definitions. Okay, let us write. It states that that for any body, physical body, the algebraic sum of the externally applied torque and opposing torques, you can say opposing torques at any instant is 0. Okay, already we know this one because we discussed in the translational mechanical systems. Or I can say sum of the applied torques is equal to sum of the opposing torques, in a simple manner you can say. Okay, sum of the applied torques is equal to externally applied torques is equal to sum of the opposing torques. Okay, so this is D'Alembert principle for rotational mechanical systems. Okay, so now we'll see like simple example. Consider a rotational mechanical system and its motion is around a fixed axis. Okay, so consider a mechanical system. Okay, the motion anyway for rotational mechanical system, the motion is around a fixed axis. Okay, right, let us see the diagram here. So this is my reference. Okay, now if it is connected, now this is my diagram. So okay, this is my system, which is connected in center, right? Okay, so this is one of the given mechanical system. Let us see, this one will be stiffness, I can say inside spring element or stiffness, I can say inside we have a stiffness here. Okay, and which is represented with what? K, right? Now this is ground here. Now in this case we have B, viscous friction coefficient. Or you can simply say damper element. Okay, so in this case damper element we have a viscous friction, right, in this particular area, friction between surfaces and fluid, right? So this term, this is inertia element, right? And torque is, let us know the inertia element, all elements are written in this case. So here see, displacement will be like this. So this is a displacement, and torque, external torque is applied like this. Okay, so this is nothing but rotational mechanical system. Okay, example of any one rotational mechanical system, right? Now see here, in this case torque is applied in this direction, right? So therefore here the opposing torque will be there, which is applied on spring element, that is taken as a TK. Here also at the dashpot or damper element we have damping torque opposing that one. Okay, so let us write equations, torque equations for this one. So from the rotational mechanical system, to write the torque equations, okay, what we need to take a free body diagram. Okay, so free body diagram already we discussed, okay, in a translational mechanical system. What do you mean by free body diagram? Free body diagram, okay, is a diagram where only we will see opposing torques and applied torques, okay, acting on a inertia element in this case, right? So just to draw free body diagram, so let us take this one. Okay, so for above given rotational system, I am writing free body diagram. Okay, so if you want details about free body diagram, okay, so go to the previous lecture of this class, okay, so that is translational mechanical system, where I discussed in detail free body diagram. What is that? Okay, so here let us draw the free body diagram. So see, this is my free body diagram, okay, and here it is inertia element, right, and this is, we have a stiffness there, I am writing as this. Okay, so this is a free body diagram for given above rotational system. Now we need to see the opposing, only you need to write the forces here, right? Opposing, torques here, right? So what is the torque here? This one will be moving like this. This is externally applied torque, okay, and torques opposing, this is, see here, dashpot will be there, this one dashpot. So here is a dashpot, see, it is opposing to, right? Okay, so this one I am writing here TB, okay, and another is opposing here stiffness, see here stiffness, okay, it is opposing the externally applied torque, right? So this one, so what can you write this one? This is TK, okay, right, TK. Now see here another external, see, for sorry once, right, see, we have opposing force whenever applied that particular torque, then opposing torque also here present, that is inertia torque. Okay, so this is also, I can name it, I can opposing one TJ, right? Here also forgotten to draw that, so here also another is opposing here, that is TJ, okay, inertia torque, right? So this is the free body diagram. So let us write the torque equations. Torque equation. So in terms of displacement we can write here, right? So by D'Alembert principle, what is we say? Summation of total torque, okay, in a body, acting on a body, is at any instant is 0. Okay, so see here, not a straight line this one, right? See here, so we will write by seeing the free body diagram. So T minus torque minus dashpot, in any order you can write dashpot d theta by dt, okay, minus spring element k theta and inertia d square by dt square theta square, okay, at any instant is equal to 0. Okay, already I told what is the negative sign indicates here, the opposing torque, okay. So if I consider this one, therefore torque is equal to in order wise I can write J d square by dt square theta square plus B d theta by dt plus k theta. Okay, so this is the torque equation for given rotational mechanical system for this system. Okay, so what we need to see for given mechanical system, okay, you need to do free body diagram. Free body diagram shows applied torque, externally applied torque and opposing torques on a acting on a inertia element. Okay, so that you need to represent. Okay, so this is our free body diagram. Okay, so after that write the torque equations, okay, using D'Alembert's principle. So how you have written this one? By D'Alembert's principle. Okay, so I written the torque equation by using D'Alembert's, based on D'Alembert's principle. Okay, so let us see another system. Right, example if I take, consider a rotational mechanical system and its motion is around a fixed axis. Okay, see, I am naming again and again, the motion is around a fixed axis. Okay, so rotational system means itself is the motion will be around a fixed axis. Okay, no need to mention again and again. So for example, I am naming like that. Okay, so let us see the system. Right, so this is a reference, and consider this is one of the inertia element. Okay, and which is consist of spring. Okay, now we'll see torque is applied here. Okay, T, and here we have theta, right, and also velocity. Okay, this is K, and here we have a ground, right. So here we have a dashpot. Okay, here we have a dashpot, and this is a inertia element. Now torque is applied like this. Okay, so this is given rotational mechanical system. Okay, so this is, as you know, reference. Okay, this is also reference, right? So for this one we need to write torque equations using D'Alembert's principle. Okay, so let us write the torque equations. Okay, now in this case let us write in terms of velocity. Okay, so for given rotational system, what we need to take, first of all, we need to draw a free body diagram. So for this one, let us draw a free body diagram before going to write a torque equation. So free body diagram for this one. See the free body diagram. Okay, now here we need to represent, this is externally applied torque. Okay, now opposing, see here in this diagram, what are the opposing? Now this is opposing torque we have, so that is I can write here Tk, and here also the damper element also opposing here, so I can write this one as a Tb, and right, inertia element itself, so this is again Tj, right. So these all are the opposing torques here in this case. So represented free body diagram means what? Only representation of applied torques and opposing torques acting on a inertia element. Okay, so this is a, say this is inertia element J, right? So all are remaining three are here opposing. What are they? TK, TB and TJ. Okay. So this is the free body diagram for given rotational system. So let us write the torque equation. Okay. So I will write by D'Alembert's principle. Okay, taking D'Alembert's principle. Okay, so what is the sum of applied torques is equal to sum of opposing torques, or in a simple manner, if I write this one, so sum of opposing and applied torques acting on a inertia element is 0. Okay, so let us take in detail from this. Okay, from this, right? Now from inertia torque, so I can say mention Tj. So what is that? So J into d by dt of velocity, angular velocity. Okay, so I am writing equations in terms of angular velocity here, right? So okay, next is for damping coefficient. Okay, so I can say Tb, which is nothing but what? B into velocity, angular velocity. Okay, don't forget to mention angular quantities here. Okay, and this one will be 1 by k integration omega dt. Okay, so angular velocity, right? This is a torsional spring element. Okay, these are the equations. So therefore the final equation, therefore the torque of a rotational mechanical system is given by J d by dt of omega plus b omega plus 1 by k integration omega dt. Okay, so this is the torque equation, okay, for given rotational mechanical system. Okay, so for this system, for given rotational mechanical system, right? So I will conclude here. In the next class we are going to discuss torque voltage analogy and torque current analogy. Okay, so it is nothing but rotational mechanical system analogous to electrical systems. Okay, so we will see the conversion of all elements of rotational mechanical systems into the electrical systems. Okay, so we will convert, we will write the differential equations there, okay, while conversion, and also we will draw the electrical network for given for given rotational systems. Okay, thank you.